Hello everyone. Welcome to the SWAM NPTEL course on mathematical geophysics. We continue with module number 3, Mathematical Modeling 1. This is the lecture 4, Equations of Gravitational Field. In this lecture, the concepts covered are related to the equations governing the gravitational field. These are the equations which state the properties of gravitational field from various perspectives. These perspectives are the integral form, the differential form, and the gravitational potential, and its application of these equations of the gravitational field to various geophysical aspects forms the fourth component of this lecture. Thus, this lecture focuses on the various forms in which the gravitational field can be expressed mathematically and the construction of a gravitational potential, which is very useful in understanding different aspects of gravitational field in a simplified mathematical manner. So, let us begin. First, we look at the integral form of the equations for the gravitational field. So the first integral equation is line integral of g dot dl equals 0. What does it mean? This is the first equation of gravitational field in integration or integral form. So this is the first equation of gravitational field in integral form. That is line integral of g dot dl equals 0. We derive the derivation. We look into the derivation of this integral form of the equation. Consider an arbitrary loop. This is a differential line element denoted by dl vector. This loop is a closed loop. Consider this as an elementary mass located at the position vector q. We consider the integral a to b g dot dl as the partial circulation of the gravitational field. Now A and B can be any 2 points on this closed loop. We denote the location of this line element dl vector as P. The distance between P and Q is LQP. Thus, the circulation can be given by minus g dm, which is the elementary mass, multiplied by integral from a to b of dl by LQP square. Now, LQP square is a function of the location P. As the location varies from A to B, the distance LQP changes. Hence, the integral can be simplified and evaluated as g dm multiplied by 1 by LQB minus LQA, since the gravitational field depends on the endpoints as it is a conservative field. One can also obtain this using regular integral calculus. Now, we have the expression of the circulation from point A to B. But since this is a closed loop and the theorem is for a closed loop, we have to estimate what happens when the circulation is evaluated over a closed path. Over a closed path, A and B will extend and coincide. Which means LQB will be equal to LQA, and this makes the bracketed term equals to 0. This gives us the proof for the first equation of the gravitational field, which is line integral of G dot dl equals 0. This renders that the gravitational field is circulation free. Now we move on to the second equation in integral form. The second equation, or the integral form of the equation, reads as integral G dot ds equals minus 4 pi gm. Physically, it means that the flux of the field over an entire closed surface equals minus 4 pi gm, where m is the mass inside this closed surface. Now, have a look at this diagram. Consider this as a closed surface area enclosing a volume V. An elementary surface area on this surface can be given by ds vector. Thus, the flux through this ds vector is given by G dot ds, where G is the gravitational field. Now we consider the mass m. This is located at the point Q, and the ds is located at the point, say, P. Thus the distance between these 2 points is LQP. From the Newton's law of attraction, we get G dot ds equals minus G dm multiplied by LPQ dot ds divided by LQP cubed. This is equivalent to minus Gm by the distance squared multiplied by the area. ds vector is the area. It is also useful to represent this as G dot ds equals minus G dm d omega. D omega is the elementary solid angle subtended by the elementary surface area ds at the point Q. For a better understanding, let us have a separate diagram. The elementary surface area ds subtends the elementary solid angle d omega at point q. N vector is the vector perpendicular to the surface area. Now we consider the total flux through this arbitrary surface area, which is given by integral of g dot ds. This is nothing but integral of the solid angle for the entire closed loop. We have omega. Now omega is, as we can recall from previous lectures, is area divided by the distance between the point Q and the surface area squared. This has been used in the previous derivation. LPQ by LPQ cubed gives essentially 1 by LPQ squared multiplied by ds, that is substituted as dw, which is then integrated over the entire surface area to get omega. Thus, the total flux, that is integral g dot ds, is minus omega g dm. Thus, the flux through an arbitrary closed surface surrounding the elementary mass is given by minus 4 pi g dm. The circle on this integral represents that this integral is being taken over a closed surface area. Now, we know that if the solid angle is measured such that the point lies within the closed surface area, then the total solid angle is always 4 pi. Thus, the expression. This 4 pi is irrespective of the surface shape and the position of Q inside the volume surrounded by the surface S. Even if the point Q is any of these locations, the total solid angle will be 4 pi. Now we use the principle of superposition, and assuming that the volume V there is an arbitrary distribution of masses, we get integral of dm equals m. M is the total mass in the volume V. So this expression is for an elementary mass, and this expression is for all the elementary masses inside that volume. So we obtain the second integral equation for the gravitational field, which is the flux equals minus 4 pi gm. Now we turn to differential form of the equations of gravitational field. These two equations are the differential form of equations for the gravitational field. The first is the curl of G equals 0. The second is divergence of G equals minus 4 pi G delta. The first indicates that the gravitational field is irrotational or curl free, and the second equation gives that the divergence of the gravitational field is negative, which means that the field lines would point inwards towards the location of the source of the gravitational field. So let us look into these in more detail. First, the derivation of curl of G equals 0. Recall the Stokes theorem, which links line integrals with surface integrals. The Stokes theorem says that the circulation is equal to the flux of the curl of a gravitational field. From previous discussion, we have obtained that integral of g dot dl equals 0. And the curl of g being a non-zero quantity, and hence this expression of curl of g dot ds equals 0 leads to curl of g equals 0. This is because for any arbitrary surface, if the integral goes to 0, then the integral quantity is 0. This is the first equation of gravitational field in differential form. This is valid at points inside and outside masses where the first derivative of the field can exist. Next, we look into the derivation of divergence of G equals minus 4 pi G delta. Here, delta is the density. We have integral g dot ds equals minus 4 pi gm from the integral form of the gravitational field, which we have discussed just previously. Denoting m as integral of delta dv, which is nothing but density into volume, we can obtain integral g dot ds equals minus 4 pi capital G into integral of delta dv. This can be given in terms of integral of divergence of G dv equals the right hand side. Now, divergence of G dv comes from the Gauss theorem. This, you can recall that Gauss theorem connects surface integrals to volume integrals where the divergence of the field is involved. Because these integrals are equivalent or equal to each other for any arbitrary volume, we can equate their integrals. This gives divergence of G equals minus 4 pi g delta. This is the differential form of the second equation of gravitational field, and it is valid for all regular points where the first derivative of the field exists. Now, what happens if the mass is located outside the enclosed area? Since this expression is valid for delta or m, which is located inside the enclosed surface, thus if the mass is taken out of the enclosed surface, this goes to 0. Thus we have divergence of G equals 0. Now we move on to a quick summary and further discussions. Gravitational field is an irrotational field which we can obtain from the differential form of the gravitational equation, that is curl of G equals 0. Next, we look into the gravitational field and its potential function. This is the result of the irrotational field property of the gravitational field. Since curl of G equals 0 and curl of any gradient is equals to 0, G can be represented as minus of gradient of U, which is the potential function. This is the property of curl, and this has been discussed in previous lectures relating identities of curl of vector fields. This gives us the Poisson's equation formulation for the gravitational potential. Since divergence of G equals minus 4 pi g delta, we can substitute minus of gradient of U in place of G to obtain Laplacian of U equals 4 pi g delta. And if the mass is outside the volume, then the gravitational potential obeys a Laplacian equation. This is the Laplace's equation applicable for the gravitational potential without any internal masses. Having discussed the various forms of the gravitational equations, we now move on to their application in geophysical studies. The gravitational potential and Earth's gravitational field are very interrelated concepts. The Earth's gravitational field is very appropriately modeled in terms of gravitational potential. The variations in density within the crust and mantle makes it suitable for representation as a gravitational potential. The gravitational potential is also used to compute the shape of the geoid and detect various anomalies in gravity which is caused by subsurface structures. This means that if this is the surface of the Earth, there may be structures which are higher density than the surrounding. This leads to the gravity anomalies, which are nothing but variations in the gravity readings which is made by surface measurements. If these are the locations where the gravity is measured, these measurements will be affected by the localized high density bodies, and result in gravity anomalies. In this case, the understanding of gravitational potential can help us to remove such noise which may be arising from geological sources and focus on the more fundamental and necessary details. Further applications of gravitational field are listed as follows. The differential form of the gravitational field is used to calculate the spatial variations of the gravitational field due to local density contrast. It also provides a framework for understanding gravity anomalies, which is caused due to the variation of density in various layers of the Earth. The differential form is also used to directly the differential form is also used to directly link measurable quantities to density distribution. On the other hand, integral form are used for forward modeling to compute the entire gravitational field from known mass distributions which are located in subsurface. The integral form is also used in global studies such as computing the Earth's geoid and the gravitational potential of the Earth. The integral form is also used in numerical simulation models to estimate the gravitational influence of complex geological structures which cannot be performed in analytical manner, and hence integral form along with numerical simulation comes to rescue. And hence integral form used in numerical simulation helps. Thus, we conclude that equations of the gravitational field are widely used to investigate Earth's internal structure and dynamics on the surface of the Earth, along with measurement of various components of gravity. The gravitational field and its equations can be used to explore natural resources. These equations are also used to monitor environmental changes such as ice sheet dynamics and sea level variations, which are very important from climate dynamics perspective. The following reference can be referred to for more details. Thank you.